about rational functions, but I want to make sure we have a couple things very well defined here. For a rational function, okay, we define them as this capital R, okay? And because it's a function, we have to make sure it's defined in terms of some variable. In this case, we're just going to use x, okay? And all it really is just one polynomial, let's call it p of x, divided by another polynomial. We'll call that one q of x, okay? Where p and q are defined as basically this sort of function right here, okay? Where we have some coefficient times x to a certain power plus another coefficient plus times x to the next power down right there. We keep adding that until we get to basically x to the first power plus 1. Okay, so basically it's any sort of function that looks like that. Typically we won't see anything higher than the second or third degree, maybe even the fourth, but usually it's things that we can factor to make life a little bit easier for ourselves. Okay, we want to talk about vertical and horizontal asymptotes. Okay, so a vertical asymptote, as you can see right here, it says as the absolute value of a function f becomes very large as x approaches some number b, then the line x equals b is a vertical asymptote of f. All that's really saying is this. If we take our denominator, our vertical asymptotes can be found where this denominator is equal to 0. So if we can identify any real zeros or real solutions of the equation q of x is equal to 0, that's where we're going to find a vertical asymptote. The other type of asymptote is the horizontal one, so going left to right. Okay, where vertical is this guy right here, like we've seen with graphs of tangents, as well as with some rational functions we saw in lesson 1. A horizontal asymptote, on the other hand, is found as x becomes very large. That input value, okay, becomes very large. So basically we want to think about this. So our horizontal asymptotes are this right here. It's basically a theory that says as x approaches some very large number, that means that that function is going to be equal to that, okay, is equal to some number a. That means that there's a horizontal asymptote at the value y equals a. Okay, we'll talk about that in limits in a little bit here, okay? So let's go ahead and take a look at an example here. F of x equals negative 2x plus 6 divided by x minus 1. Once again, it is a rational function because we have a polynomial. Technically, they're just linear polynomials, but they're polynomials nonetheless, and one is divided by the other, okay? So for domain and range, remember, domain is all of our x values and range is all of our y values, okay? So we want to look at domain. We want to start at both of them. Domain is always going to be x is equal to all real numbers. And then for range, we want to define that as that y is equal to all real values, okay? And we always use that as a starting point for both, and we want to use our function, just the definition of the function, to kind of whittle away any pieces of our function that we can consider not part of it. Those are our restrictions, okay? So that's what we're going to do with our asymptotes, is we're going to try to find some restrictions in both sets of the domain and range. So the first thing we want to do is look at our vertical asymptotes, okay? So we're going to put into practice what we saw here. We're going to take our denominator, which is x minus 1, and we're going to set that equal to 0. So x minus 1 equals 0, okay? When we solve that equation by adding 1 to both sides, we get that x is equal to 1. That means that there is a vertical asymptote in this graph at x equals 1. It's a vertical line at that value there. That means we can go back to our domain and say that x is equal to all real numbers except x cannot be equal to 1. Okay? So that pretty much solidifies our domain for the reason being that we know, because we solved the equation here, we know that it cannot be any number besides 1. It's just not defined there. And the reason is that if we replace 1 in our denominator here, 1 minus 1 is 0. that means that we can't divide by 0. So the only value that makes the denominator 0 is 1. Okay. Now looking at our range, once again, here's how we find our horizontal asymptote here. We're looking at this next slide here. So our horizontal asymptote, remember, the idea behind a horizontal asymptote is that we want to make x become very, very large. Okay? And whatever value we get out of that, it is going to be our horizontal asymptote. So when this happens, any constant values, we can basically ignore at this point. So we can get rid of our constant values and look at the two leading coefficients on both of these terms here. So we have -2 here and +1 technically right here in front of our 1. So then as x approaches a very large number, we say that it's going to approach the value -2 divided by 1, or just -2. Okay? So then that means that our range, if we go back up to our first slide here, if I can get my computer to work, that means that our range is all values of all real numbers except y cannot be equal to -2. Okay, and once again, you can use technology to verify this, that there is indeed you can never get to -2 on this graph, and you can't get to x equals 1 because of the restrictions we have set up here. Okay, so now let's look at a different example here. We have the next function, which is f of x equals x divided by -x plus 2. Okay, so once again, just like we saw in the last one, we want to start by saying our domain is all real numbers. Same with our range. Our range is all real numbers until we can prove otherwise. Okay, so now we're going to find, in the next slide, we're going to find all asymptotes. We're going to kind of go back and forth here. Okay, so our first asymptote is our vertical ones. So vertical asymptotes, this guy right here, we're going to find it by setting our denominator equal to 0. So -x plus 2 equals 0. We just have to solve that equation here. Subtract both sides by 2, we get -x equals -2. Therefore, if we divide both sides by -1, we get x is equal to +2. So because we have x equals 2 as one of our vertical asymptotes, we can go back and amend our domain. Instead of just saying all real numbers, now we can say that our domain is all real numbers except x cannot be +2. Okay. Same thing with the range. We want to find the horizontal asymptote back at our values here. So if we look at our function, we're going to erase this, erase that circle. We're done with him. And once again, the idea behind a vertical asymptote is that we want a horizontal asymptote is that we want x to approach a very large number. And like I said in the last problem, we take out anything that's a constant, anything that's a lower degree than what we started with, or than our leading coefficient. And what we want to do is we'll examine the leading coefficients here. So we have +1 here, technically we have -1 here. So we do 1 divided by -1, which gives me -1. That means that there is a horizontal asymptote at the value y equals -1. So then once again, we can go back and amend what our range is. Okay, so it's no longer just all real numbers. Our range has to be all real numbers except y cannot be equal to -1, just like we saw in the previous slide. Okay? Looking at a much larger polynomial here. Okay? So now we're looking at quadratics in both numerator and denominator. So we're going to find range, domain, and all of our asymptotes. So in order to do that, in order to determine what our domain and range is, we're actually going to do this in reverse order. We're going to find all of our asymptotes first, and then we're going to go ahead and find our domain and range from there. Okay, because we can always assume until we prove otherwise that our domain and until we find our asymptotes, we can then amend our domain and range. We have to be able to prove otherwise though. So we're going to assume that domain and range are real numbers, all real numbers, and then we're going to kind of once again whittle away there. Okay. First thing we want to do whenever we have quadratics or any sort of higher degree polynomial, we want to be able to factor and make our life a whole lot easier. Okay, so I'm going to factor both numerator and denominator here. So if we look at x squared minus x minus 12, once again, we want to find factors of 12 that add up to negative 1. And in this case, because 12 is also negative, that means that we have to find one positive factor, one negative factor. And that's going to be negative 4 and positive 3. So we factor this to be x minus 4 times x plus 3. Now the denominator, it has a common factor here. Common factor for 2x squared minus 2x minus 4, and that's going to be 2. So I'm going to take out a 2 here and divide all these by 2, and that's going to leave me with 2 times x squared minus x minus 2. Okay? Now, we can factor the quadratic that's in the denominator here. We're looking for factors of negative 2 that add up to negative 1. In which case, that's going to give me, if I keep my numerator the same, so x minus 4 times x plus 3, all divided by 2 times x plus 1 times x minus 2. Okay? Now, looking at our factored form here, there really isn't much that cancels out, so we have to look at our denominator first to find our domain. Okay, so our domain is once again all real numbers. In order to determine what our restrictions are, we have to set the denominator equal to 0. Okay, so we're going to say 2 times x plus 1 times x minus 2 equals 0. And we have to set all of our factors equal to 0 in order to find out what our restrictions are. All right, so that includes 2. So we say 2 equals 0, x plus 1 equals 0, and x minus 2 equals 0. So going from left to right, we're going to solve these equations. 2 equals 0 is a false statement, so we can just go ahead and toss him away. X plus 1 is equal to 0. That means we solve it by subtracting 1 from both sides. We get x is equal to negative 1. So there's one of my restrictions. And then we solve the second equation, x minus 2 equals 0, by adding 2 to both sides. Therefore, we get x is equal to positive 2 as another restriction here. So we have two vertical asymptotes in this case. One is at x equals negative 1, and the other is a vertical asymptote at x equals 2. So our two vertical asymptotes are x equals negative 1 and x equals positive 2. Okay. Now we look at our range. And in order to do this, we need to look at our original function, because we want to make sure that we know what happens when we get to very large numbers. And like we've said already, when we have very large numbers for our range, we take the original function and we look at only the first two terms that have leading coefficients. Okay, we want these two. We want to take a look at these guys. This one, in terms of large numbers, all those terms I just crossed out, the x, the 12, the negative 2x, the negative 4x, they don't matter when it comes to very large numbers. Okay, so as x approaches a very large number, we'll say as x approaches infinity, we're looking at x squared divided by 2x squared. Well, because we have x squares, we can cancel these out, and we're left with 1 divided by 2. That means as x approaches infinity, that means we're getting closer, that output value is going to be 1/2. So there's going to be a horizontal asymptote at y equals 1/2. Okay? And that's how we answer that question. Okay? So now, here's how we figure out our domain and range. So our domain is going to be all real numbers, except x cannot be -1 or +2. And then our range is going to be all real numbers, except y cannot be 1/2. All right, so this wraps up our notes on rational functions for now. Please make sure you stay tuned for part 2 on linear functions and piecewise functions. We will see you next time.